Hello everyone and welcome finally to Calculus 1, summer of 2020. My name's Dr. Rossi and I'm glad to be teaching the course and glad to have you as students. I've spent a lot of time in school, not just as a professor but also as a student. And as a student, I spent a lot of time in class, not just during fall and spring, but during summertime also. And you know what? When I look back on all of the courses that I took during the summer, by far my most enjoyable courses and the courses that I learned the most in, I took during the summer. The weather's nice, things are kind of laid back, but you still get a lot done. And we're not cramming Cal 1 into 4 weeks this summer. We've got almost 10 weeks to do Cal 1. The weather's going to be nice. We're going to take it at a good pace, but we're going to get a lot done, and we're going to enjoy it. Make sure we get a lot done. Work hard, but let's make sure we enjoy it too. And we are going to learn a lot. So again, welcome to Cal 1. This is our first lecture in Term 5, summer of 2020. And we're going to start right off with a motivating example. We're going to consider the function f of x equals x squared. And I have a table of values, x values and their corresponding f of x values. And I'd like you to think about something. As we move from left to right at the top of the table, what is x doing? As we move from left to right across the top of the table, what is x doing? Probably you're thinking that x is getting bigger, and it is. But can we say anything about the way in which x is getting bigger? If we continue this table, is x going to get bigger in the sense that it's going to take off to infinity? Doesn't look like it, does it? X is getting progressively larger with each entry. But notice how it is that x is getting larger. It's getting larger, 1, 1.9, 1.99, 1.999, 1.9999. It's getting larger, but it's getting larger in a way that the x values are getting closer and closer to 2. They're getting closer and closer to 2. But it also looks like these x values are never actually going to get there. They're getting closer and closer to 2, but they never actually get there. For example, if we had to make a guess what number would appear next on the table for x, it would probably be a 1 with 5 nines, right? 1.9999. And the corresponding y value, 3.99996. So x is getting larger and larger, and it's getting closer and closer to 2 as it does. But it never actually gets to 2. So here's what I'm going to do. Right above this table, I'm going to write that. which means that x is approaching 2. It's getting closer and closer to 2, but it never actually gets there. Now, the next thing that we want to consider is, as x gets closer and closer to 2, what is f of x doing? Well, we have 1, 3.61, 3.96, 3.996, 3.9996, 3.99996. As x gets closer and closer to 2, the f of x values, they're getting bigger, but they're getting closer and closer to what? 4? So here's what I'm going to do. I'm going to write f of x approaches 4. Now, let's look at this table of values on the bottom. And as we move along the table, this time from right to left, what are the x values doing? 3, 2.1, 2.01, 2.001, 2.0001. The x values are getting smaller, aren't they? But they're not getting smaller in the sense that if this table is extended, the x values are going to go to negative infinity. It's not going to happen. The x values are getting progressively smaller, but they're getting smaller in such a way that the x values are getting closer and closer to what? 2? The x values are getting closer and closer and closer to 2, but they're never going to get there, are they? If we had to guess what the next entry in the table would be, our guess would probably be a 2 and not 3 zeros and a 1, but 4 zeros and a 1. If I had to guess what the next entry on this table would be, I'd say 2 and 4 zeros and a 1. And the corresponding y value, 4.4 zeros and a 4. So as we move along the top of the table from right to left, x is again approaching 2. This time from the right. X is approaching 2 from the right through values that are larger than 2. So let me use my blue marker here. X is approaching 2. It's getting closer and closer to 2 from the right, but it's never, ever, ever going to get there. And as x gets closer and closer to 2, what is f of x doing? Let's look. 9.0, 4.41, 4.04, 4.004, 4.0004, and so forth. As x approaches 2 from the right, f of x gets closer and closer to 4. So I'm going to write this. F of x approaches 4. Now take a look at this example, study it. Notice what the x and y values are doing, or the x and f of x values are doing in each case. We're going to refer back to this example on occasion as we introduce a mathematical concept. Now, there are two ways to describe what's going on. One way is, as x approaches 2 from either direction, f of x gets closer and closer to 4. And that's a good way of describing what happens. There's also another way that we can describe what's going on. We can say that we can make f of x as close to 4 as we want by making x sufficiently close to 2. For example, f of x is darn close to 4 right here. Let's see, how far off are we? Tens, hundreds, thousands, 10,000s, 4 100. We're only 4 100,000ths of a unit away from 4 here. That's pretty close to 4. But suppose that we wanted to get even closer to 4. Suppose we wanted f of x to be even closer to 4 than this. How would we make that happen? Well, just make x closer to 2, right? If we make x closer to 2, let's see, 1, 2, 3, 4 zeros. Let's put 5 zeros here. Two 5 zeros and a 1. F of x is now 2 5 zeros and a 4. F of x is 4 rather. 5 zeros and a 4. How close is this value of f of x to 4? Only 4 1/millionths of a unit away. So we just made f of x even closer to 4 than it was before, just by making x closer to 2. Now suppose that we want to make f of x even closer to 4. What do? Just make x even closer to 2. Maybe 2 6 zeros and a 1. And then f of x will be 4 and 6 zeros and a 4. So f of x would be 4 10/millionths of a unit away from 4. So we can describe what's going on one of two ways, and both of these are good ways of describing what's going on. We could say that as x approaches 2 from either direction, f of x gets closer and closer to 4, and that's definitely what's going on. We can also say this. We can make f of x as close to 4 as we want by making x sufficiently close to 2. Both of these are very good ways of describing what's going on. And mathematically, we have a way of defining this behavior. mathematically, here's how we describe the behavior. We say the limit of f of x as x approaches 2 equals 4. So 4 is the limit of f of x as x approaches 2. And this is how we write it mathematically. When we see this statement, here's what we say. We say the limit of f of x as x approaches 2 equals 4. And just so that we leave no doubt about what's being said, the limit is this number 4. The limit is the value that f of x is getting closer and closer to. Now, this is how we describe and define the behavior of the function that we just saw in the tables that were on the board. What I want to do now is generalize these statements to any situation. Okay, we're going to talk about the limit of a function f of x in the general sense. The statement, the limit of f of x as x approaches c equals L, means that as x approaches c from either direction, f of x gets closer and closer to this number L, which is the limit. So, the limit of f of x as x approaches c equals L means that as x approaches c from either direction, f of x gets closer and closer to L, the limit. Now, there's another way of interpreting this, and both of these ways are good ways of interpreting this statement. The limit of f of x as x approaches c equals L means that we can make f of x as close to L, the limit, as we want by making x sufficiently close to c. Remember in our example, 4 was the limit, and we could make f of x as close to 4 as we wanted by doing what? We could make f of x as close to 4, the limit, as we wanted by making x sufficiently close to 2. So in general, if we say the limit of f of x as x approaches c equals L, what that means is that we can make f of x as close to the limit as we want by making x sufficiently close to c. And before we go on, I have to make a disclaimer because I don't want to get sued. You know, I hate lawsuits and all of that sort of thing. But this is going to turn out to be a very important disclaimer. And here it is. When we say that x approaches c, we mean that we can make x We mean that we can make x as close to c as we want, but we also stipulate that x can never actually become equal to c. X is approaching c here. What does that mean? It means that we can make x as close to c as we want, but we stipulate that x can never become equal to c. Remember in our example, x was 1, 1.9, 1.99, 1.999. X was getting closer and closer to 2, but it never actually got there. And then from the other direction, x was 3, then it was 2.1, then 2.01, then 2.001. X was getting closer and closer to 2 again, but it never actually got there. So this is what the limit means. And both of these are good explanations as to how we interpret this statement. I'm not going to say favor one over the other. What I'm going to do is say each one of these expresses what's going on very well, and each one says a little bit that the other doesn't say. So it's really good to have both of these understandings of limit. Well, we've given the definitions. What do you say we actually do a real live example, okay? Okay, everybody, real live example. Compute the limit of x squared plus 2 as x approaches 5. And let's identify what this is. The x squared plus 2, that is our f of x. So, how can we compute the limit of x squared plus 2 as x approaches 5? We could create a table of values like we did in our opening example. And that would give us a pretty good idea of what f of x gets close to as x gets close to 5. We don't want to rely on that method if we don't have to, because sometimes the limit of a function, the value that a function is approaching, may not be a whole number. And it may not be obvious what the tables, what the values of f of x in our tables are getting close to. So creating tables of values was good for our opening illustration, but we don't want to have to rely on that. So since I can't think of anything else to do, I'm just going to take the value that x is approaching and plug it into f of x. Okay. The limit of x squared plus 2 as x approaches 5 equals 27. What do you think about that? I'm wondering if that bothers anybody's mathematical conscience. I can remember when I was a student in calculus, occasionally I'd see some things that would bother my mathematical conscience. I'd see it and I'd say, well, that just doesn't seem right. Or I'd see it and say, well, that doesn't seem fair. Like fairness is an issue in mathematics. Well, that's the way I felt. But whether my conscience was right or wrong, occasionally I'd see things in math that bothered my, quote, mathematical conscience, end quote. This may be one of those things that bothers our mathematical conscience, and maybe it should. Those of us whose consciences are bothering us right now, this may be the reason. When we gave the definition of limit and we talked about x approaches c, or in this case, x approaches 5, that we said that we can make x as close to c as we want, or x as close to 5 as we want. But we also stipulate that x never becomes equal to c, or x never becomes equal to 5. When we say x approaches 5, we're saying we can make x as close to 5 as we want, but at the same time, we're stipulating that x never actually becomes equal to 5. So to compute the limit of x squared plus 2 as x approaches 5, what did I do? I made x equal to 5. I plugged 5 in for x. I violated my own definition of limit. And when we break the law, there are consequences. I think this is a case where I broke the law. So we need to be aware of the fact that technically what I just did was illegal. You know, it seems like I'm hung up on this word today. Stipulate. Oh well. My vocabulary's not working, so I can't think of a synonym. Yep, we just violated the definition of limit. We violated the stipulation that x can never become equal to the number that it's approaching. There are going to be consequences. We break the law, there are consequences. And when we plug a number in to compute the limit, we're breaking the law. So the plugging in method of computing a limit will at times yield an invalid result. Okay, bad news and good news. When we plug in, we may at times get an invalid result because we're violating the definition of limit. The good news is, as long as the plugging in method doesn't yield division by zero, the result is valid. Well, why is that good news? It's good news because if we plug in and we don't get division by 0, the result's valid. Oh, but what if we do get division by 0? Hey, if we get division by 0, we'll look at it and say, hey, I'm dividing by 0. This isn't going to work. I better try something else. See, we know we can't divide by 0. So if we plug in and get division by 0, we move on to plan B. But if we plug in and we don't get division by 0, the result's valid. So that was nice. It turns out that the decision on the field stands. The limit of x squared plus 2 as x approaches 5 is in fact equal to 27. Our result was correct. Yep, we broke the law when we plugged in 5 to compute our limit. But we didn't get division by 0, so the result's valid. And technically, even though we're breaking the law by plugging in to compute the limit, it's so easy to plug in a number and compute that that's always the first thing that we do when we compute a limit. We plug in. And if we don't get division by 0, we say, good, that's our limit. And if we do get division by 0 when we plug in, we say, this isn't right. We got to go to plan B. When we do calculus, we want to be able to compute limits. But just as importantly, when we compute a limit, we want to make sure that we understand what the limit is telling us. So here, $27 is our limit. And what does this mean? One take on this is to say that our function f of x, and this is our f of x, so we can make our function f of x and we know what f of x is. Let's see, x squared plus 2. We can make our function x squared is 2 as close to 27 as we want. And see, 27, that's our limit. So we can make f of x as close to 27, our limit, as we want. By making x sufficiently close to 5. You want x squared plus 2 to be really close to 27? Just make x really close to 5 and it's going to happen. That's what this statement is telling us. Now there's another way of interpreting this, and I like both of these ways. I don't favor one above the other. I think they're both very good. And I think sometimes one says something that the other doesn't. So here's the other way to answer that. Excuse me. Pardon the interruption. Here's the alternative take on what this limit means. It means as x approaches 5 from either direction, right? So in this context, x squared plus 2 is our f of x, and 27 is our limit L. Both of these are very good ways of interpreting this statement. This statement, limit of x squared plus 2 as x approaches 5 equals 27, means that we can make x squared plus 2 as close to 27 as we want by making x sufficiently close to 5. That's a great way to say it. Alternatively, limit of x squared plus 2 as x approaches 5 equals 27 means that as x approaches 5 from either direction, our function x squared plus 2 gets closer and closer to 27, the limit. That's what that means. We don't just want to be able to compute limits. We want to be able to understand the results once we compute them. And by the way, give yourselves a pat on the back because we are officially doing calculus right now. When I took calculus, people who hadn't had calculus would say, well, what is calculus? And I'd say, it's derivatives, it's integrals, you find largest values of functions and smallest values of functions. You add up infinitely. It's a lot of things. It's not just one thing. And nobody really bothered to tell me what calculus was. I knew what calculus sort of included, all the topics it included, but I didn't see the big picture. So I was never able to give an intelligent answer when somebody, or I was never able to give, let's say, an insightful answer when somebody asked me, well, just what is calculus anyway? The best way to define calculus is to say that calculus is the application of something called a limit. Limits are at the base of everything that we do in calculus. Everything that's in our calculus text in some way or another is tied into limits. So an insightful answer would be to say, well, calculus is the application of something called a limit, or the study of limits and its applications. We've just computed our first limit, so we are officially doing calculus. Now, let's go on to another example, okay? Let's compute the limit of that function. What's the first thing that we always do when we compute a limit? We plug in because it's so easy. Yeah, it's illegal, but as long as we don't get division by 0, we're okay. Let's see, 4 times 3 is 12, minus 4 plus 4, 12. Okay. We didn't divide by 0, so our result is valid. Well, that was easy. Let's see, what does this mean? It means that as x approaches 2 from either direction, our function gets closer and closer to 12, the limit. And alternatively, it means that we can make this function as close to 12, our limit, as we want, just by making x sufficiently close to 2. We don't want to lose that perspective. So first thing, try plugging in. Yeah, it's illegal, but it's so easy that if it works, we just have to let that be the first thing that we try. So we have negative 3 squared, that's 9, plus 9 is 18. No division by 0, our result is valid. We'll do this because we want to make sure we never forget what the interpretation of a statement like this is. So there's our result from the preceding exercise. How do we interpret this? What's one way of interpreting it? One way is to say as x approaches 3 from either direction, f of x gets closer, whoops, what is f of x? X squared plus 9, that's our f of x, isn't it? F of x, x squared plus 9, gets closer and closer to our limit 18. So that's one interpretation. We want to be conversant in both interpretations. Let's see, what's the other way of looking at this? We can make our function as close to the limit as we want by making x sufficiently close to that number. So again, we can make our function f of x as close to the limit 18 as we want by making x sufficiently close to -3. And we definitely want to keep both of these viewpoints, both of these interpretations of what a limit is. Now, let's do another example. Nah, I don't want to do that. How do we start this off? Plugging in, right? That's always our first option. Okay. 9 minus 12 is negative 3, plus 3 is 0. And 9 plus 12 is 21, minus 21 is 0. Okay. The red flag should be going up and down here. Okay, we got an invalid result. But did it hurt us? No. Here's the invalid result. But we look at this and say, wait a minute, division by 0? No, that's no good. See, when we plug in and we get division by 0, we can never be fooled into thinking that we got the right answer when we have the wrong answer. If we plug in and we get division by 0, we're always going to know this is invalid because we can't divide by 0, and we know what division by 0 looks like. So the plugging in method is the first step, is great. If we don't get division by 0, the result's valid. If we do get division by 0, we look at it and go, okay, no good. I'm not going to be fooled into thinking that this is the correct result. I know it's not because we're dividing by 0. Time to go to plan B. So the next thing that we do is we try to cancel a common factor in the numerator and the denominator. Okay, how does the top factor? Does that work? Let's see. We multiply these together, we get 3. We get negative x minus 3x is negative 4x. Yep, looks good. And now on the bottom. Does that work? Multiply those, we get negative 21. This gives us 7x. This gives us minus 3x, 4x. Yep, we're good. Okay, we have top and bottom factors, and we want to cancel out the common factor. And this is definitely going to work. I'll tell you why. What is this factor equal to when we plug in x equal 3? This factor is equal to 0, isn't it? So this is the factor that was making the numerator equal to 0 when we plugged in x equal 3. And what's this factor equal to when we plug in x equal 3? It's 0 also, isn't it? So this is the factor that was making the denominator equal to 0 when we plugged in x equal 3. Now you may be asking, well, is it legal to divide top and bottom by x minus 3? If x is 3, x minus 3 is 0. So is it really legal to divide top and bottom by x minus 3? Aren't we dividing by 0? And the answer is no. Because remember something. X is approaching 3, but it never gets there. And since x never actually becomes equal to 3, x minus 3 never actually becomes equal to 0. So we can divide top and bottom by this common factor. Okay, we got rid of the troublemakers. We canceled the common factor in numerator and denominator. Now what? We still don't have our limit. But since we got rid of the troublemakers, the factors that were equal to 0 when we plugged in, since we got rid of these troublemakers, why don't we try plugging in now? We got rid of the troublemakers, so now we can plug in. Three minus 1 is 2. 3 plus 7 is 10, or 1/5. Here's our answer. And how do we interpret this? One of two ways. We can either say, as x approaches 3 from either direction, this function gets closer and closer to the value of 1/5. Or we can look at it this way. We can say, we can take this function right here and make it as close to 1/5 as we want just by making x sufficiently close to 3. Yeah, okay, that looks good. What's the first thing that we always try? Plugging in. Okay, we have 4 minus a negative 8, so that's 4 plus 8 is 12, minus 12 is 0. And on the bottom, 4 plus negative 4 is 0. Okay, we got that division by 0 again. No good. But that's okay. If we get division by 0, we know what our next step is. I think maybe I need to get spell check for my whiteboard. There's probably only one L that's supposed to be here. So try canceling a common factor in numerator and denominator. Maybe we can do that. How is this going to factor? Let's see. 2x minus 6x is minus 4x. That looks good. And son of a gun, I feel kind of silly now. X plus 2 is one factor, but I see clearly now the other factor is just x. Okay. And we do have a common factor. Zip, zip, we cancel both of those. We got rid of the bad guys. So now we can plug in. And once we plug in, we don't need to have this limit operator here. By plugging in, we're actually computing the limit. So I'm just going to take negative 2 and plug it in for x. And we have negative 8 over negative 2 is 4. I'm going to make a remark that may be helpful, especially if we're computing limits involving polynomials of degree 3 or higher. Probably we don't have much trouble factoring quadratics, second-degree polynomials, but we might have to deal with a third or fourth-degree polynomial and have to factor that, and it may be challenging. I'm going to tell you something that may make that a lot easier when we're factoring polynomials in order to compute a limit. This is something that we probably learned in high school. I probably was exposed to it in high school. And it was one of those things that we spent a few days on, maybe in our sophomore or junior year. And then we never ever saw it again. Never had an occasion to use it. And now it's 3 or 4 years later. And if we ever were taught this, we certainly don't remember it because it's not like we had an occasion to apply it after we learned it. I don't remember having this in high school. I'm sure I did. But, we probably were taught it on one day, and the next day, and the next day we did some exercises using this fact. And for several years after that, I just never saw it again. So when it came time for me to make an application of this, I didn't, because I didn't even remember that I ever knew this. And it's probably the same way with most of us. But here's the scoop. If we have a polynomial, p of x, and c is a number such that when we plug it into the polynomial, we get 0, then guess what? X minus that number is a factor of the polynomial. You saw me factoring the polynomials in the previous exercises. This is exactly what I was doing, because in our exercises, we had a number that we could plug into the top and into the bottom and make them both 0. And so I said, okay, x minus that number has to be a factor. That's what I was doing when I was factoring the polynomials in the preceding 2 examples. Now let me just give an example here. Now, let me see. If I plug 2 in here, what happens? Let's see. 2 squared is 4 times 3 is 12. Whoops, bad example. Yes, let's let this be the polynomial. 3x squared plus 2x minus 16. If I plug 2 in here, I get 2 squared is 4, times 3 is 12. Plus 4 is 16, minus 16 is 0. Since we can plug 2 into this polynomial and make it equal to 0, so x minus this number is a factor. And let's just check. I claim that x minus 2 is a factor. So it ought to be pretty easy to find the other factor. Let's see. Whatever goes here, I have to be able to multiply it by x to get 3x squared. So this has got to be 3x. And whatever goes here, I have to multiply that by negative 2 to get negative 16. So I guess an 8 has to go here. Now, let me just check it. X times 3x is 3x squared. And negative 2 times 8 is negative 16. But do we get 2x as the middle term? Let's check. Negative 2 times 3x is negative 6x. Plus 8x is 2x. Yep, that works. Well, let's do another one. Okay, what happens here? We get negative 3 squared is 9, minus a negative 15, that's plus 15. So 9 plus 15 is 24. Minus 24 is 0. Okay, we just learned something about our polynomial. Negative 3 makes this polynomial equal to 0. So x minus negative 3 is a factor. X minus a negative 3 or x plus 3 is a factor. Okay, let's check. Supposedly x plus 3 is a factor. So what would the other factor be? Whatever goes here, I have to be able to multiply it by x to get x squared. So I guess x has to go here. And whatever goes here, I have to be able to multiply it by 3 to get negative 24. So it looks like x minus 8. And let's just check. X times x is x squared. 3 times negative 8 is negative 24. Now, 3x minus 8x, negative 5x. Yep, that works. So, I was using that trick when I did the previous examples. I used that trick to factor top and bottom. Let's look at one more example. Now we'll look at several more examples. How about that? What's our first step? Try plugging in. Okay, let's see what we got. 1 minus 4 is negative 3, plus 5 is 2, minus 2 is 0. And 1 minus 1 is 0. Yep. No good. Division by 0. So we go to plan B. And what is plan B? Cancel a common factor in top and bottom, if we can. I like it better that way. So let's factor this son of a gun. Oh, this is a cubic. How do I factor that? I already know what one factor is, because if I plug x equal 1 in here, I get 0. So x minus that number has to be a factor. X minus 1 has got to be a factor of this monster. Now, can I figure out what else goes there? Whatever is here, I have to be able to multiply it by x to get x cubed. So this has to be x squared. And whatever goes here, when I multiply it by -1, I need to get -2. So I guess this has to be a +2. Now, I just have to make sure that whatever goes here will give me -4x squared and +5x. So let's see. Whatever goes here, let's look at the x squared terms. X squared times -1 is -x squared. But I have a -4x squared up here. I'm missing a -3x squared. So whatever goes here, I have to multiply it by x to get -3x squared. So I'm thinking -3x. Let's check it out. -x squared minus 3x squared, -4x squared. Yes. Now that's all I need to do. But to be on the safe side, let's make sure that I get this term as well. So we'll look at the x's. 2 times x is 2x. Plus 3x is 5x. Beautiful. Yep, we factored that correctly. And this thing, well, again, since we plugged 1 into this polynomial and got 0, x minus 1 is a factor. And we know what this is anyway. It's the difference of perfect squares, so this has to be x plus 1. And we cancel away. And now that we've canceled, we can plug in. Okay, 1 squared minus 3 times 1 plus 2. Son of a gun. 1 plus 1 is 2. So we get 1 minus 3 is -2, plus 2 is 0. And 1 plus 1 is 2. Ooh, we got 0 over 2. Well, wait a minute. Is that really such a big deal? If we divide by 0, we got problems. But we're not dividing by 0 here, are we? We're dividing 0 by something that's not 0. When we divide 0 by a number, what do we get? We just get 0. Okay. So, no problem. That's our limit. As x approaches 1, this function gets closer and closer to 0. Or to look at it another way, we can make this function as close to 0 as we want by making x sufficiently close to 1. Now, this was a good example for a number of reasons. One, that we got experience factoring a cubic polynomial when we plug in and get 0 in numerator and denominator. And we needed some practice using this trick. Secondly, this is a good example because we ended up with 0 in the numerator, but a non-zero in the denominator. And we realized, you know what? This is no big deal. It's just 0. So, before we move on to yet another example, let's make sure that we recognize the significance of this point. Zero in the numerator, that's not a big deal. It's no problem. The only time 0 is a problem is when we have it in the denominator. So we saw this thing, and probably the first thing we did was we panicked. Oh my God, we canceled, and we still got a 0. Well, it's a 0 in the numerator. The 0 in the numerator never hurt anybody. Now, there's one other kind of exercise that we need to look at before I end the lecture and bury you up to your eyeballs in homework. No, I'm just kidding. I will give you some homework, though. But we do need to look at one more type of example. And before we see the example, I have to define something. We're defining something called a radical conjugate. So we have a pair of radicals that we're adding or subtracting. And if we're adding, the radical conjugate of square root of a plus square root of b is square root of a minus square root of b. given the radical pair square root of a minus square root of b, the radical conjugate square root of a plus square root of b. In both cases, all we did was we changed the sign in between. And if we only have one radical, we'd consider square root of a minus b to be the conjugate. And if we have square root of a plus b, we'd consider the conjugate to be, if we have square root of a minus b here, we'd consider the conjugate to be square root of a plus b. So again, we just change the sign in between. Now, there's a reason why I'm telling you this. A radical pair and its conjugate have interesting properties. And right about now, some of us are probably looking at this and saying, you know, I've seen something a lot like that before. Like maybe we've seen x plus y and x minus y. And what did we get? We got the first thing squared minus the second thing squared. Yeah, this is the factorization of the difference of perfect squares. And when we multiply this together, we just get the first thing squared minus the second thing squared. Well, here's x and here's y. When we multiply these two things together, the same thing is going to happen. We're going to get the first thing squared minus the second thing squared. That's what happens when we multiply a radical pair by its conjugate. Now, what's so special about this expression? There are no radicals here. There are no square roots here at all, and that's significant. multiply a radical pair by its conjugate, we get an expression that contains no radicals. And we're going to need to use this fact in the next exercise, because the next exercise has a radical pair. Let's look at it. What do we always do first? Try plugging in. Okay, we got the square root of 9, which is 3, minus 3 is 0, and 2 minus 2 is 0. Okay, this is getting to be a familiar theme. Our next step is that we try to cancel, but I don't see a common factor in top and bottom. And yet it turns out that there is a common factor. There's some factor common to the top and bottom, such that when we plug in x equal 2, we make that factor 0. And I think I know what the problem is. This radical is preventing me from grouping and combining the terms in the numerator in such a way that that factor becomes apparent. Now, I don't think the denominator's a problem. I think this is the factor that I want to cancel in the denominator. Because when I plug in 2 for x, I get x minus 2. And this is my 0 factor in the denominator. So I'm thinking, hidden among all of this garbage in the numerator is a factor of x minus 2. I just can't get at it because this radical is preventing me from regrouping and combining the terms so that the factor of x minus 2 will be visible to us in the numerator. And as long as I have this radical in the numerator, there's no way we're going to get at that factor of x minus 2 in the numerator. So we got to get rid of this radical. How do we do it? Well, remember, if we multiply a radical pair by its conjugate, all of the square roots disappear. So that's what we're going to do. We want to multiply the radical pair in the numerator by its conjugate, and we do that. But that means we also have to multiply the denominator by its conjugate. And let's see what we get. We get the first term squared minus the second term squared and in the bottom, you know what? I'm not going to multiply all of this junk out in the bottom because I know that this is the factor that I want to cancel. And so I'm going to keep it isolated. I'm going to write it like this. X minus 2 times this garbage. And let's see what I get. The first thing squared, that's just going to be x plus 7 minus the second thing squared, that's 9, all over x minus 2 and square root of x plus 7 plus 3 x plus 7 minus 9 is x minus 2. There's the common factor. There's the factor of x minus 2 in the numerator. We got rid of the troublemakers right here, didn't we? So now we can factor. Now we can plug in. Okay, so I got 1 over square root of x, which is 2, plus 7, plus 3. So let's see, square root of 9 is 3, plus 3 is 6. There will be some exercises like this in the homework, and there will be an exercise like this on test 1. So know how to do an exercise like that. If you look on my website at all of the practice tests that date back, some of them to the 1980s, test 1 always has one of these problems with the radical on it. So make sure that we know how to do a problem of this type. And I'll tell you something. This is how we get 100s on our tests, 10 points at a time. If we know something's going to be on the test, learn how to do that kind of exercise. And that's an easy 10 points counting toward the 100 that we're going to get on that test.